All right, let's talk about Google's huge new quantum announcement. They've unveiled a processor codenamed Willow, and in this explainer, we're going to break down what this leap forward really means.
Quantum computers are supposed to be these incredibly powerful machines, right? But for years, there's always been this one nagging question. What if they're just too fragile, too full of errors, to ever actually be useful for real-world work?
Okay, so to really get why this breakthrough is such a big deal, you first have to understand the massive problem that all quantum computers are up against.
It really boils down to two giant hurdles. First, can they actually solve useful problems faster than a supercomputer? And second, can we even trust the answers? You see, for the longest time, these two things felt like they were at war with each other. Pushing for more speed just seemed to make them more error-prone, and making them more reliable, well, it just slowed them right down.
And that's where Google's new Willow processor comes in. This thing is a huge deal because it represents a moment where for the first time, we're seeing one device tackle both of those massive problems at the exact same time.
So you gotta understand, Willow's success isn't just one breakthrough. It's really two giant leaps forward packed into one. One leap for getting a useful speed-up on a real scientific problem, and another for proving we can actually build reliable machines out of these, well, pretty unreliable parts.
All right, let's dig into that first leap, the verifiable speed-up. This is all about proving that quantum computers can finally be practical, not just some cool science experiment.
And that word right there, verifiable, that's the key. See, in the past, we've seen claims of quantum advantage on some pretty abstract math problems. This is different. This is about solving a meaningful scientific problem faster than anything else on Earth, and getting results you can actually repeat, trust, and interpret.
So what do they actually do? Well, they ran this super clever algorithm called quantum echoes. The best way to think about it is like a kind of high-tech sonar. You send a pulse into a quantum system, you let everything get scrambled up, and then you try to perfectly reverse time to see how well the echo comes back. It's a really powerful way to measure how information spreads out in these incredibly complex systems.
And the result of that experiment? A 13,000 times speed up. Yeah, just let that sink in for a second. That is the advantage Willow had on this specific and really valuable scientific task.
To put that number into perspective, check this out. The calculation took Willow about 2 hours to run. If you try to do the same thing on Frontier, and by the way, that's the fastest supercomputer on the planet, it would take an estimated 3.2 times years. I mean, that's not just a little bit faster, that is a genuine practical quantum advantage.
Okay, so speed is great, but a fast wrong answer is, well, it's still wrong, isn't it? Speed is totally useless without accuracy, which brings us to Willow's second, and you could argue even more important breakthrough, taming those quantum errors.
Now, the idea here, quantum error correction, or QEC, isn't new. The theory's been around for decades. You basically take a whole bunch of your fragile, error-prone physical quantum bits, qubits, and you kind of gang them up to protect one piece of information, creating a single, super robust logical qubit.
But here's the billion-dollar question that has kept scientists up at night for years. Does it actually work in the real world? I mean, does making the system bigger make it better, or does it just make it noisier? Because if adding more qubits just adds more errors, the entire field hits a dead end. Game over.
And this is the proof. For the very first time on this kind of chip, Willow showed that scaling up works. They built a logical qubit from a small 3x3 grid and measured its error rate. Then they scaled up to a 5x5 grid, and the error rate dropped. Then they went even bigger, to a 7x7 grid, and the error rate dropped exponentially. This is it. This is the experimental proof we've been waiting for. Bigger really is better. This is basically the green light that the entire quantum computing world has been waiting for. It confirms that the underlying physics is sound. The path to a truly fault-tolerant quantum computer is no longer a physics problem. Now, it's an engineering challenge. A massive one for sure, but an engineering challenge nonetheless.
So, okay, we've got a proven speed up and a proven path to reliability. So what? What can we actually do with this thing, like right now?
Well, it turns out that the very same quantum echoes algorithm they used for that speed test can be used as a brand new scientific tool. It basically acts like a molecular ruler, letting scientists measure the tiny distances between atoms in a way they never could before. And this has immediate, real-world implications for stuff like designing new drugs or inventing brand new materials.
Now, it's super important to remember that this Willow chip didn't just appear out of thin air. It's a critical piece of a much bigger, much longer-term roadmap that Google has been working on for years. So if you look at their roadmap, you can see Willow's success checks off a huge milestone. But even more than that, its error correction results give them the hard data they need to push forward. It proves that the next big step, building a logical qubit that can live for a long, long time, is actually possible. All of a sudden, that ultimate goal of a million-qubit machine, well, it starts to look a lot less like science fiction and a whole lot more like an engineering plan.
Okay, so beyond that useful molecular ruler calculation, the team also ran another, more abstract test, just to really push the chip to its absolute limits. And the sheer scale of the computation they were able to do, well, it led the head of the lab, Hartman-Neven, to bring up a pretty wild and pretty controversial idea from theoretical physics.
You might have seen headlines about this, suggesting that this experiment proves the existence of parallel universes. Look, it's a fascinating thought experiment, for sure, but it's really, really important to draw a line between the hard, peer-reviewed science and the philosophical speculation. That multiverse stuff, it was in a blog post, not the scientific paper. The experiment itself doesn't prove or disprove the many worlds idea. The real story here, the core scientific facts, are that 13,000x speedup and the groundbreaking error correction.
So what's the big takeaway from all of this? It's simple, really. Willow has proven that the fundamental principles for building a useful, scalable quantum computer are sound. The game has changed. The race is no longer about solving a physics puzzle. It's about tackling a massive engineering challenge. The question isn't if we can build one anymore, it's how long is it going to take.